Thanks for coming, Diana.
Good evening, everybody.
I don't think
Is this?
Oh, yeah.
Hello? Check. Hello, everybody. Is that coming through? All right. My name is James Weir. I'm the Vice President of the Washtenaw Bird Nature Alliance. It's great to be here with you. Thank you all for coming. I know you're not here to listen to me, so I'll keep my remarks brief. Our president, Matt Spoor, sends his regards. He's doing some conservation work down in Toledo and also not feeling so well, so he couldn't make it here tonight, but he asked me to say hello to everybody, and thank you all for being here as well. Just want to promote a couple of events we've got coming up. On Saturday morning at 10 a.m. at Lake Erie Metro Park, we are going to visit the Hawkwatch site that is operated there every fall. The Hawkwatch coordinator, who sort of manages that for the park, will speak to our group at 10:30, give us a brief overview of that nationwide conservation effort to better understand raptor migration and keep accurate counts. It's been going on for many years at Lake Erie Metro Park and a number of other places across the country. So that's from 10 to 12 this coming Saturday. It's also during Hawkfest, which is the park's annual sort of event about the Hawkwatch. So there's going to be lots of other activities. There's usually tons of experts there. It's a great opportunity to learn about raptor migration and just meet nice people. So hope to see some of you there this Saturday. We're also going to continue to do our Monday night migration walks at Mathai Botanical Gardens. Those start at 6 p.m. in October and will shift to 6 p.m. in September, and will shift to 5:30 beginning in October. So I see many of you out there have already joined us for some of those, and I hope you'll continue to come, and some of you will join us as well. Juliet Berger continues, our past president, continues to run Thursday morning walks at the ARB during migrations. Those start at 8 a.m. And then we are also organizing a shorebird trip on September 28th that will be posted on our website in the next day or two. As you all may have noticed, it's been a very, very dry September here, and we're hoping to get some rain so that some good shorebird habitat pops up some of the fluttles in the countryside and along the farm roads and things of that nature. So stay tuned for that. We'll have that online in the next day or two. Last thing I'll promote is our program next month. Our treasurer, Keith Dickey, who in addition to being a financial whiz who helps keep this organization financially sound, is also a fabulous bird photographer and recently took a trip to Panama. So he has put together a presentation with lots of good photos and information about that trip and the great species of birds that he saw. And that is here at 6 p.m. on October 15th. So I want to thank Kate Jackman, our program chair, for putting this all together, as well as Victor for his help, the district library staff. Thank you very much to the experts up there helping keep everything running. And lastly, I'd like to thank Ramamurthy for today's presentation. So go ahead and come on up, and thanks very much for being here, everyone.
Yeah, I got this one.
Okay, cool.
Good evening. All right, this is my first time giving a talk here. This is all pretty strange to me. I've never had any contraptions like this before, so, but I now don't even feel it. And in about 10 minutes, I won't even know it's there, so. All right, this is a relatively new topic. I'm a rookie in this business of birdsong, vocalization, bioacoustics. In 2023 December, I was directing a camp, co-directing a camp, young birder camp in India. And one of the topics, one of the masterclass that was being taught at that time was bioacoustics. And I was fascinated. And I said, well, let me get into this because there's a lot of theory there, which I loved. And long time ago, I had some involvement with the business of sound when I was working for Ford Motor Company. So felt relatively comfortable getting into it. So since then, I've actually developed a deeper interest into it, and so I'm going to share some of my thoughts today. And I have about 60 minutes, right? Got it. All right, I'm not going to read the whole thing. I'm not a newcomer to Washtenaw Audubon. I mean, I'm sorry, Washtenaw Bird Nature Alliance. Sorry about that. It's tough. In fact, I was wearing the wrong T-shirt this afternoon. Then I said, oh no, this is not going to work. The wrong T-shirt and the correct hat. And I said, no, that won't work. And so I had to go dig this out and ironed it, and I'm wearing it today. So I've been a birder since 1978, and so as I mentioned, I'm relatively new to this field. But I did teach a master class for young birders at Cave Creek, Arizona. I had about 15 kids, and we spent 10 hours in the class and 10 hours in the field. And we had some phenomenal vocalizations that we recorded, and then we brought it back into the lab, into the class for analysis and so on. And so I have actually transitioned in the last few years from being a casual birder who would actually go places to see birds and appreciate birds and observe them and so on. And now I've gotten more serious into the study of birds. I'm still interested in birds, but I don't necessarily, I'm not out there birding. So that's my new thing. And I'm also expanding my taxa. I'm going to spend several days at the northeastern part of India, almost near the Chinese border, studying moths. And then I'm going to bring back, they're going to send those moths into the laboratory in Pune, and I'm going to be learning for the first time how to do genomics of moths. So those are my newer interests right now. So anyway, today the topic is bioacoustics, and we'll focus on birds, of course. And we will talk about what sound is. I have one slide. And we'll also talk about, we'll have to get some definitions out of the way. We'll talk about what is bioacoustics. And then I just have one slide in the interest of time to talk about why do we study bioacoustics. And then we have to have another definition, which is what is a songbird? We use that word all the time. But are all songbirds, do they sing? And so what makes a songbird a songbird? We'll go into a little bit more about the physiology of bird sound itself. And we'll also just touch on why do birds vocalize. Just like we have a reason to communicate with people, when I say hello to somebody, or when I'm saying anything to anybody, I have a reason for it. There's a context. And it's exactly the same thing with birds. They also have a context on why they vocalize. And then I'll make the case of why should we consider visualization of birdsong. There are other well-known, time-tested classical methods for listening, but why should we look at use of technology to study birdsong? And I will go through some illustrations, and then I'll definitely take questions. I'll be here, no worries there. So let's just get into definitions. Sound is nothing but a pressure wave. It's a longitudinal pressure wave. That means the sound is traveling in the direction in which it's supposed to be going. So it's got rarefactions and compressions, so it's a pressure wave. So the subject, which is at the other end, which could be your ears, which is actually a recorder of sorts. It's a microphone and a recorder connected to the brain. Or it could be a shotgun microphone connected to a recorder. Or it could be a parabolic reflector collecting information and then onto a recorder. So these pressure waves go and hit these diaphragm of, let us say, the ear, or the shotgun microphone, or the parabolic microphone. And then this pressure has got rarefactions and compressions. So essentially, the graph is a very cartoonish thing at the bottom. It's the pressure, air pressure, measured in kilopascals versus time. That's what's actually recorded. But it has to be converted into something much more useful in order for us to know that this particular sound that we heard is from a specific bird. So we'll get into that. There is math involved there. I'm not going to get into the mathematics here, but there is math here which actually converts this into a usable form. It's actually something called fast Fourier transforms. So we'll use that method to convert them into spectrograms and waveforms. And that's what's actually useful. All right. And then, of course, we use software for it. And I have some good news for that software. Raven Pro is from Cornell. Today, Raven Pro, you have to subscribe to it. But I would say in about a month or so, it's going to go free. Raven Lite is free. In fact, everything that I'm going to show you today, you can actually do it with Raven Lite. But Raven Pro is something where you can do a lot more sophisticated things. I'm beginning to learn them myself, and that's going to go free, thanks to some large grants that Cornell has had. And so, but of course, if you are from a developing country, Raven Pro has always been free for folks in the developing countries, plural. So let's get some definitions out of the way again. Lots of definitions here because we are talking about this topic, at least for me, I'm talking about this topic for the first time here. What is this business called bioacoustics? It's not necessarily connected to birds. I personally know researchers who study whales and dolphins. I know folks who study elephants. And I know, of course, people who study birds and crickets and also bats. And array of taxa over the entire insect species. There is a lot of work that goes on, and I know a few researchers in each one of these taxonomic classifications. So there's a lot of definitions out there for bioacoustics. Let's just focus on the last two. It's a scientific study on how animals and humans produce and transmit and receive sound. Right? It's about that mechanics of how these things work. It also deals with sound production of animals, the information content of the sounds produced, and their significance in the ecological context. That's what's exciting for folks who study bird sound. And today it's a pretty sophisticated field. Started in the early 50s in the US with pioneering research in New York, and later on in Cornell and in Stony Brook and so on. And today it's studied across the world. Right. All right, let's look at taxa and classification of where these frequencies are. The audible range of frequency is 20 hertz to 20 kilohertz, although I'm going to be actually playing you two examples of a bird that you can easily recognize out here. It's a warbler, and it also migrates during fall migration and during spring migration. You will know it when you see it, but it's tough to hear, especially as we get older. It's a lot harder to hear. And I'll show two examples of birds that we see routinely in spring and fall migration, but it's not so trivial. I'm going to just play those, and don't tell me if you heard it or you didn't hear it. I'm just going to play it. So, but there are birds which actually produce sounds in the ultrasonic region, in the greater than 20 kilohertz. And of course, there's no chance that we will have bats do that. But there are some birds like the Ecuadorian hill star, the parrots, the rock wren, the rufous-faced warbler. So you would see them vocalizing, but you would not hear them. And that can happen to the two examples that I'm going to present as well. But then, on the other side, there are always going to be exceptions, right? And so birds are nothing different. So the cassowaries and the western caperelli are also vocalized, but they vocalize in a range that we can't hear, like elephants do. Elephants, when they are communicating, we don't hear them at all. But unless you are able to record the low-frequency sounds and bring it back into visualization, then it's easy. Bats, you can easily record them, and you can bring it back into, with technology, within seconds, you can actually see it actually communicating. Elephants, the same thing. So, yeah, the albatross are known for the infrasound during migration. They actually pass cues for migration to their other neighboring birds. That's how they communicate in the infrasound, that is less than 20 hertz. Okay, here are two examples. And let's see if I have luck. I've had luck with this, and I'm going to try and play the first one. And this is a warbler species, and I'm sort of giving you some hints. It's from the Parullidae family. that most of you have seen. I'm not giving you any color and morphological information here, size, shape, and it's definitely seen during spring migration and fall migration. If you hear it, it's awesome. Were you able to hear that? Any guesses? The two guys up there who helped me to set this up, we were testing this, and the gentleman there said, hey, this is a 10 kilohertz. He did not know what that bird was. It's a blackpoll warbler. So that's, this is also another bird, but from a different family. It's not a warbler. I'm going to go ahead and stop this. Can you hear this? Golden crowned kinglet. I'm sure all of you have seen it during spring migration. It's also at the edge at about 9,600 and above is where it's vocalizing. Again, the gentleman back there, he knew exactly what that frequency is. He's a sound engineer, by the way, so he absolutely nailed it. Anyway, these are birds which are typically vocalizing at very, very high frequencies. And most of the birds that we do here, like the cardinals and the chickadees and the wrens and so on, the blue jays, they're all within the 20 to much less than 10 kilohertz. And we'll play some examples of that. What is this business of bioacoustics being used for today? Researchers are using it for monitoring species. Like, for example, Tucson Audubon has passive acoustic recorders all over the deserts to study occupancy. Do we see these birds? Are they declining? Are they even there? In fact, just 2 days ago, a buddy of mine in India rediscovered a bird after 75 years. That bird had not been seen. He had actually installed the passive acoustic recorders across a huge swath of the forest, and they heard the recording for the first time in 75 years, the Jordan courser. So it's great news to see that these are not actually extinct. These are still there, right? And I'm going to get started in this business of monitoring species with black swamp early spring next year. So I'm going to get into that business of analysis and also monitoring species occupancy and so on. Lots of analysis there. And understanding ecosystems. I'm not going to go read everything, but it's another application of bioacoustics today, and monitoring climate change. So lots of papers, lots of research papers involved in studying acoustic signals at a given place over a period of time to see what is actually going on in this world. With the change in climate, you have change in habitat. It also means that there's a considerable change in biodiversity. So this is another reason why one would study bioacoustics, because you can't always be there to look at these birds and do census and so on. So you have to rely on systems like this. Today, you can buy a recorder for $200, and the battery will last you for about 3 to 4 weeks, and you can actually program it in such a way that it will record just the first 15 minutes of a day, or you can set up the intervals and so on and so forth, and you just bring back the SD card, and you're all set to do analysis and so on. And there are more sophisticated ones as well. So, all right, moving along. And why are we interested in sounds at all? And I'm sure one or more of these would resonate with you. It evokes emotions. When we listen to music or bird sounds, especially when you're on a trail, when it's kind of peaceful and you're listening to these birds in spring or in fall, not as much in fall, but mostly in spring or in summer. It influences our moods, provides a sense of connection, allows us to relax, and so on. So one or more of these would be something that you can actually sort of agree with. So now let's just get into some definitions again. What are these songbirds? How do birds get their song? Is there any relation between our current understanding of how birds learn to our current understanding of how children learn? Is there a parallel between those two? And again, these were studies in the 1960s by Peter Marler in New York, where we have tremendous amount of information today on our understanding is so sophisticated today on how birds learn their learn their song. Why do they vocalize? And I've just got one slide, and then we'll go through a couple of videos on birdsong mechanics. Let's illustrate that as well. Okay, so this is actually, if you go and Google birds on a wire, you will actually get this. And somebody has taken the piano and actually played this tune for this thing, and it's fascinating. Of course, the birds here have no clue that there is actually a note that's there, several notes. But if you go and Google birds on a wire, you will get this. And I'm not going to go ahead and play this. It's about 2 minutes long. It's a piano composition based on these tunes. And they'll actually follow these little notes that are there. So check this out. But the thing that I want to talk about here is not all songbirds sing, and not all singing birds are songbirds. Oh, that's interesting. So a songbird is a very special classification in the business of ornithology. It has to belong in the family of passeriformes, the order. Order is aves. The next classification down is the family, which is the passeriformes. There is about 6,600 birds in that group. That's about almost 60%, right? Let's say there are, give or take, 11,400 birds. There are about 6,600 of them are in the passeriformes, but they're not all songbirds. So, for example, the American crow is in that same family, but then we have to learn one more thing beyond knowing it belongs to a certain family. Let's see what that is. It belongs to the order passeriformes, and then they are classified into two groups, the oscines and the suboscines. And the suboscines are about 20% of that 60%, right? And so oscines are the largest group of the passeriformes family. In that is also the crow. But I would agree, I'm sure you would agree with me, that a crow is not one of those birds that you would recognize for having a melody. But melody is not the basis for classifying a bird as a songbird. Songbird is based on the fact that it is an oscine or a suboscine. So specifically, a songbird is one which is considered to be an oscine. So what is the difference between a bird which is considered to be an oscine and a suboscine? The oscines include all your jays and the finches and the blackbirds and the tanagers and so on. All the flycatchers are in the suboscines, and we'll see that the oscines have a very complex vocalization structure compared to a very simple structure of the suboscines. In the next slide, I'm just going to play two examples, and you can tell me whether it's an oscine or a suboscine. I think, no, it's not in the next slide, 2 slides from now. So remember, an oscine has a much more complex vocalization structure compared to a suboscine. But there's one more thing that we need to know. An oscine must learn a song. It doesn't come when it's born. It does not come with a song. It comes with a template to receive a song. But it does not have a song. But the flycatchers, on the other hand, are genetically programmed. They come with a song. That means they don't learn anything else. But these guys, the oscines, have actually got to learn. All right? So there are some things that I'm going to talk about which are not in these slides because I don't know how much time I have, so I'm always conscious that it's going to be only 60 minutes. So, okay. With the oscines, I said it has to learn. That means it has to learn from who? From its parents or from its neighbors. So the experiments that were conducted in the 50s and 60s is they took the oscine birds, the white-crowned sparrow, one of the most well-studied bird for analysis, and they actually took it away from its parents. They put it in isolation. The song that it develops is what's called an isolate song. It's nowhere even close to what a white-crowned sparrow would sound, right? In fact, The white-crowned sparrows will never recognize it, and it's too late for it to go learn when it's an adult. On the other hand, they did experiments with flycatchers, where they actually surgically removed, we now know today in the neural structure of these birds, which component of the brain is involved in sound creation and listening. We know both. So they turned off the listening portion for flycatchers. They still sang what they always sang. They're genetically programmed. They come with a song, and that's what they stay on. But there's one more nuance with the signs. Yes, they learn. I have a slide which talks about the process of learning, but the signs, there are some of these signs have they're eternal learners. It's not like they learned in the beginning and then they stop learning. That's what most of the signs are. But the song sparrows are a classic example, extraordinarily well studied in the US, and they are ones which will learn forever, right? And the zebra finches, the same thing. So they keep learning, they listen, and they learn. I don't want us to get confused between bird vocalization and their song with mimicry. That's a whole different topic, which I'm not even going to touch on today. I'm not going to talk about mimicry at all. Oh, not me. I'm trying to turn it off. I'm sorry, folks. Did not intend. I hope it shuts off itself. Yes, thank you. Okay, so signs must learn their song from scratch, but sub-signs are genetically programmed. We just talked about that, and we talked about some nuances of that as well. All right, so I'm going to play two different vocalizations, and we'll talk about this graph that I'm showing you, which is a spectrogram. I'm going to explain that in some detail. This is what you get when you take the pressure versus time data and you do fast Fourier transform analysis. You get two things, and this is one of those, which is the spectrogram, which is frequency as a function of time. Time is on the x-axis, frequency is on the y-axis. Going up is higher frequency. I'm going to play both of them, and you can tell me whether it's an sign or a sub-sign, and I'm sort of giving you some more hints here. I'm giving you the range maps. That means these are US birds. You can see where the breeding is, which is the orange section. This is Cornell maps. The orange section is the breeding place, and the migration is the yellow. This is the standard Cornell convention, and the non-breeding, the wintering grounds are out in the south, right? Both of them are kind of similar in terms of their migration patterns and their range map. Let's go play them. Okay, that's one bird. And hold on to that in the memory. Remember, all signs have a complex vocalization structure, and the sub-signs are the ones which have a simple structure which is genetically programmed. Which is a sub-sign here? The one at the bottom. It's the alder flycatcher. And the one above is something that most of you have seen, which is the magnolia warbler. And I just thought I would get this out of the way. So when you hear something, somewhat of a complex thing, then you know it's an sign. So when I go out birding now, I'm so sensitized to, especially when a cardinal is singing, you all hear the same notes, but I hear something extraordinarily fascinating, and we'll talk about that in actually a video that I'll play. And you'll never look at a cardinal the same way again when you know that for a fact. All right, let's go on. Oh, okay, I just have to move on. Okay, I just have one slide on the learning process. This is for signs. And I have not yet told you what makes an awsign, other than the fact that the output, the sound output, is more complex. That's all I've told you. But I've not told you physiologically what is so special about this awsign business. We have not talked about that, which is coming up in a few slides. So there is, as soon as the chick is hatched, there's something called a critical learning period. It lasts a year, less than a year. Bird listens to the adults and the birds around them, and the syllables are learned. And we'll talk about what is the definition of the thing called syllable. There's a thing called syllable, note, song. So we have to define all of those. When we have to study vocalizations, these are simple things. And of course, many of you have practiced music. This must be extraordinarily elementary to you. But anyway, I was never trained in music. I wish I was, at least the Western classical music. So those of you who've been trained in Western classical music, you know exactly what I'm talking about. Then there is something called the silent period. Up to 8 months, syllables are learned and stored into a template and without practice or rehearsal. Then there is something called a silent period, which creates something called the plastic songs. So practice period like infant babbling, this is practice without communication. So it's sort of trying to test it all out. Then finally, the song crystallization happens later on. A young bird converts the plastic song into a real song by selecting syllables and perfecting them into correct patterns and singing. So it has to be in constant company with its own flock. Otherwise, it'll actually get their songs very distorted. Having said that, there are song sparrows out in the east. You can see song sparrows in Maine, and you will see song sparrows in California. They're both awsigns that both have complex structures. But what we will not talk about today is something called dialect. Oh, but we do know human dialect. At least in America, we know there's dialect all over the place. You just have to go, about 200 miles south. You will already pick up, different dialects, right? Same thing. Song sparrows have so many dialects, and they are all very local. And within a park in Channel Islands, it's a national park in California, just outside Oxnard, or there, or Santa Barbara. There, within that one island, there are song sparrow communities which all have different dialects. Right? It's so very interesting, and you cannot pick that up easily by your ear. You need to record them, and you got to actually bring them into the spectrogram, and then it becomes extraordinarily clear. And I'll give you one more classic example from around here, where the Merlin ID will have no idea which bird it's actually listening to, and I'll talk about that in a minute. So this is, in a sense, how an awsign, actually the process of learning for an awsign. All right. I did talk about the fact that birds vocalize with a context. Context matters. Songs typically for territory, defending a territory, or attraction. And calls are typically alarm calls, flight calls, contact calls, begging calls. I'm not going to go into the details of each one of them, but these are all different contexts where you get these types of calls. Bird vocalization studies involves an understanding of the context of songs and calls. One of the things that I learned when I was actually learning for the first time how bird vocalization is studied is it's very well known in the literature called ethograms. Ethograms are where you actually observe a behavior and you document what it's actually trying to do. So if you go and Google and do ethograms, you will get examples for kids in zoos, studying dolphins, studying penguins, studying elephants, and so on. And you can actually categorize, bin these different behaviors that you observe, and then you say, hey, what's it actually doing? That's how bird song is studied. When you have to associate context to a bird, it's just not made up. It's because of tremendous amount of work that's gone in with ethogram studies on how these calls mean something. The context matters. So today is an extremely well understood topic. The next thing I want to talk about is mechanics. how do ossines have this complex structure? What is so special, right? At least the ossines, the ones that we associate with melody and so on, right? It all comes down to this. Where is our voice box? It's in the larynx, right? It's right here. Where do you think the bird's voice box is? It's up here at the bronchi, where our two bronchi go to the lungs at the junction of the two bronchi. That's where the syrinx sits. And the syrinx, the syringeal muscles, are extraordinarily well developed in ossines compared to subossines. Subossines also have a syrinx, but their syringeal muscles are not that well developed, and they don't have that kind of control. So that's why they don't have complex songs. So let's just go. This is straight from Cornell. See, the syrinx is right here. Right there. That's the syrinx. And that's the external view, and those are the syringeal muscles. But it gets even more interesting. And I have two illustrations. As I said, once you listen to this video, once you watch this video, you will never see the cardinal the same way. Let's watch this.
It's a paired structure. It has two sides to it that are equivalent in their ability to generate sound. And a bird actually can produce one sound on the left side and another independent sound on the right side. When a cardinal sings a beautiful upward sweep whistle, it's actually using the left side to produce the lower portion of that whistle, and without any obvious break to us as human beings, it produces the higher pitched portion of that whistle with the right side. Just amazing physiology involved in sound production.
So they don't have two syrinxes. It's the syringeal muscles have independent control on either side. What's amazing with the cardinals they've shown is where within a note, where the low frequency is coming from one side, the high frequency is coming from the other side. Let's just look one more example, also from Cornell. Let's look at the wood thrush. You can see that the high frequency signals are coming from the right-hand side, and the low frequency signals are coming from the left-hand side. They're coming independently and at the same time. Birds are the only ones that can actually sing two notes at the same time. Think about that for a second. And we have no idea that the cardinal is doing all this. Once I learned this, I cannot see a cardinal the same way as I've ever done before. All right, just thought I would leave that. I'm not going to any more details. But how do we study bird vocalizations? Because I still have to make the case for visualizing birdsong. Because we have a classic time-tested method for studying bird vocalizations. But I still have to make the case for visualization. Well, let's see. How do we recognize a bird by its vocalization? A classical approach is something called birding by ear. All of us know this. Some of us are extraordinarily good in this. Some of us are not. It involves learning to recognize the unique sounds that different bird species make and using this knowledge to locate and identify them in the field, right? Agreed? All right. What does it entail? It entails us to focus on distinguishing between various songs and calls birds produce, right? People who are very sophisticated in this can actually pick up on this. This involves studying and memorizing the characteristic sounds of different bird species, much like learning a new language. Birding by ear involves considering factors like pitch, tempo, rhythm, repetition. Think about all this. All this is a part of the sound that's coming to you, but you got to internalize all this without any visualization. It's tough for somebody who can actually recognize a bird to say, this is the reason they recognize that bird. So we do something else. We say, we do this. We say, no, don't worry about this. There are common mnemonics that black-capped chickadee is chickadee, American robin. But this is awesome. But when you come from a different country, like me coming from India, I don't hear it the same way as you do. You know, which one? This one was shocking to me when I heard this for the first time. Tea kettle, tea kettle, tea. What? Tea kettle? I don't even drink tea. So seriously, you know, it is good when it works, right? But this is, trust me, in India, they have, for their birds, they also have the same thing. You know, they also have something that people are used to the sounds that they're used to, and so on. And who cooks for you? I had a rough time trying to sort of see who cooks for me in that vocalization. So anyway, so I'm not trying to be critical of this, but anyway, I'm just trying to point out it may not universally work for everyone. But why should we consider? Yeah, that's the case. That's the whole reason why I signed up to give this talk. It's a graphical notation of birdsong. Is a challenging area of research. Remember that bird on a wire? To convert every one of the songs that we know, like the cardinal and so on, into a notation, like what we have in sheet music, is still a research that's going on. It's been done for a few birds in Stony Brook, but we are still a long way off from converting that into sheet music, like we know. Visual cues for recognition. So software-assisted visualization helps with visual cues. Like you can say, this is fast, this is slow, this is loud, this is not loud, this is high, this is low. You can see it. Then visual comparison of bird songs, same birds at different geographical locations. You know, when you can sort, you cannot probably make out easily by hearing, but when you bring that into the software, you can actually see it very, very clearly when you do analysis. And remind me if I forget, I don't have a slide today. I will talk about every one of you I know use Merlin, because that's today your the best bird guide that you have. You know, anytime when you are out there, you have a guide with you, right, who's going with you. But how does Merlin work? How does it actually know this bird? Within milliseconds, it actually recognizes the bird for you. But what's it actually doing? Well, remind me or ask me that question, because I don't have a slide. If I forget, remind me, I'll bring that up before we leave. And similar looking birds only distinguished by their song. Okay, I will show you the case of two birds in our area. Both are subausines. That means that they don't even have a complex structure. But when you see that, you will Merlin will tell you it's a trails flycatcher. Trails flycatcher is a general name. There is nothing called a trails flycatcher. But Merlin will call it trails flycatcher. But I've also worked with BSBO. I'm on their board, and I've done a lot of work at their banding station. When you catch one of these in their nets, when you catch one of these flycatchers, they would not mark it down as a trails flycatcher. They will actually put that as either a willow or an alder. But how do they know? Because there's no easily morphological differences that you can actually distinguish. But the birds, when it's in your hand, they don't vocalize. In spring, they will not vocalize. They're stressed in a way. They will not vocalize. Okay? Merlin has no help for you. It could, but it doesn't. But how do banders actually mark this bird down? This is one, when they get this bird, you're adding 4 to 5 more minutes to their workflow. You talk about the process flow that they have for processing this bird, because the whole idea is to get the bird out, because you want to stress that as little as possible. You got the bird from the mist net and you got them in the bag, you got to get them out. First in, first out. I mean, there's my mentor in the back. He will completely appreciate that we follow lean thinking when we process in bird banding labs. Totally, with no influence from me. I've had nothing to do with it. It's been done for a long period of time. because the whole idea is not to stress the bird. That's our customer. You got to get that bird out back in the field because it's probably got babies in the nest. So it's got to go back, right? Okay. So what they have to do when this bird shows up in their nest, they actually have to take wing measurements. Then they have to go and look into a manual. For those of you who are statistically inclined, they have to study the wing lengths and they have to see the confidence bands and regression lines. They have to do all of that in 4 minutes. They're trained to do that. It's bookmarked. So they flip it to that place and they'll make the measurements really quick on the wings and they'll say which confidence band does it actually fall, and then they'll classify them as alder or willow. But today, with acoustic signals, vocalization, it's a piece of cake. I'll play both in a minute. So by the way, I know a professor at the University of Chicago in the Department of Ecology, Trevor Price. His entire life's work is in the Himalayas, in learning biodiversity in the Himalayas. And his classical study on speciation of leaf warblers in Himalayas is extremely well known. And you cannot distinguish any of these birds by looks or morphology. You simply can't do it. Genetically, yes, but that means you got to get the bird and get the blood sample and so on and so forth. Genetically, no problem. But you don't have to catch the bird, but you can actually study its vocalizations. So leaf warblers today are easily studied by vocalization. And Merlin today is pretty sophisticated. It can actually distinguish all these leaf warblers in India. All right, this is the tale of two flycatchers. It's not a complex song, is it? Because it is a subausine, right? It's a flycatcher. We already learned that. What you cannot distinguish in the field, it's extremely easy. Merlin, I think in the next update of the Merlin, you will actually see it won't classify that as trails. It'll classify that as willow or alder. Those of us who follow Merlin website, they put out once a quarter, they put out a request for all their members saying that these are the birds that we need more vocalizations for. And of course, in areas like Southern America and Central America, there is a lot more requests for birds and vocalization. But US has been extremely well studied, but there are still some requests for specific birds and their vocalizations and so on. Okay. Having said that, now how am I doing on time?
12 minutes.
So 12 minutes, see? Thank you for that warning, 12-minute warning. That's an entire quarter, isn't it? Yeah, 15 minutes, yeah. Active monitoring of bird. There are two types of studying vocalizations. You can actually study it actively. That means the bird is singing, you got the recorder of some sort, either Merlin or whatever, and you're recording it, and you got the vocalization. That's active. But then you cannot be in the deep jungles early in the morning and so on and so forth, like the Jordan Corsair that I talked about. You don't know where it is. In a large stretch of land, you set up what are called passive acoustic monitoring. And I'll show you one example of that from a place that I'm going to be visiting in about 2 months. All right, so 2 ways. But before we get there, let's understand what does visualization entail. Would you like to sit on this side, ma'am? Because I know the sun is actually bothering you. Awesome. So when you get the sound from a source and you record it, it's still pressure versus time. But then the Merlin app receives that and does Fourier transform analysis. And it gives you 2 things. Merlin gives you just one thing. It just gives you the bottom piece, which is the spectrogram. It doesn't give you the waveform. Waveform is nothing but the amplitude, the strength of that vocalization as a function of time. And the bottom is the actual frequency spectrum. And I'm going to play this in a moment, and I'm sure you're going to recognize this. What bird is this? Let's play again. Northern cardinal. That's the northern cardinal. Okay, but then what is this thing? I told you this is amplitude, just the strength of that signal as a function of time. The bottom is frequency, but the frequency is so complicated. You see that there is brighter areas and lighter areas. As you go higher, the amplitude decreases, and the frequency is, of course, going up, but the amplitude decreases. Actually, these are called harmonics. I'm not going to go into the physics of harmonics here, but there is the base frequency, which is the frequency which is very bright at the bottom. The rest are all harmonics. And in fact, if you go do research on harmonics, the melody of a song has got a lot to do with harmonics. So I will not go into the physics of harmonics or the melody and so on and so forth. I'm studying it myself. But this is how you visualize a bird song. Very simple. As I told you, you can do that today with free software. Raven Light can do it right now. You can bring in a file. I would suggest you have one of the most powerful recorders in your hand, which is either an Android or an iPhone. You can use Merlin. And Merlin uses what's called a WAV format, WAV format, as opposed to MP3. MP3 is extraordinarily poor in quality. WAV format is so superior. And Merlin incorporates the WAV format for capturing sounds. So it is extraordinarily powerful to bring it into the software today. You can do that in 15 minutes after you upload this app into your laptop. They don't have a phone version yet. You can upload that into your laptop. 15 minutes later, you could be visualizing one of the songs from outdoors within minutes. All right. Let's learn a little bit of components. There are notes, syllables, phrases, songs, and song repertoire. Note is the simplest element of a vocalization. Syllables are a combination of notes. A combination of syllables is a phrase, and a combination of phrases is a song, right? So an Austin will have just about all of them. And song repertoire is a bird which has got many different songs. A bird which is actually around here. How many of you have seen the brown thrasher? Oh, that's good. Brown thrashers are local, right? It has a repertoire of 1,100 individual songs. That's the brown thrasher for you. 1,100. You heard me correct. 1,100. That's the brown thrasher. Do you know which state has its as a state bird? Georgia. I'm going to skip in this. So when you actually, with Raven Light, you can do that today. You can do measurements. This is a chestnut-sided warbler. I'm going to play that. You can what I've done is, in order for us to listen to the vocalization carefully, we are going to slow it down by 3/4. So this is actually at 3/4 speed. It's not the real speed. And so it's very useful to study these different notes in a different forms. They have got names for this. This is called a down slur, the one on the last. This is an up slur. This is an over slur. That's an under slur. These are all technical names used for in bioacoustics today. So let me go ahead and answer that question, which I asked myself. What is Merlin doing when it's actually getting an input? It's already got a wave file, it's processing, it's doing its Fourier transform, and it's actually going and taking each one of these notes, just like what I've shown you here, and it's doing this Excel spreadsheet, and it knows what the distance between the notes should be. It knows what the low and the high frequency limits are. It knows the power associated with each one of them. It has all of that information prior. And Merlin does one more thing. When you open up Merlin right now in Ann Arbor, it knows where you are. It knows more than that. It knows based on eBird, it knows what birds to expect at this time of the year at your place. So it is not looking for all the birds of the United States or the eastern part of the country, but it's looking at those birds that are expected in Washtenaw County, in Ann Arbor, at this time of the year, what birds are likely. Okay, then you are working with a very small data set. And within that, it's actually doing this analysis in milliseconds. That's what is actually giving you this information to say, yeah, this is what's going on. This is the bird that you have. All right. And so this is the alder versus the willow flycatcher. Very different analysis. So today you can actually distinguish. You don't have to call this as a trails flycatcher anymore. With acoustic signals, you can actually distinguish this very easily today. All right, passive acoustic monitoring. It's non-invasive. You can set it up and you can walk away. You can program it, and you can get different levels of sophistication for it. And it's used for survey bird populations, biodiversity monitoring, study climate change, and so on and so on. And the software that's available for it, for analysis, which is free, which you can download today, is called BirdNet. BirdNet uses a different math compared to what Merlin does. Merlin does fast Fourier transform. But this does deep learning. It's got a whole different model. It has completely different math on how it takes the input and analyzes this differently, but it still gives you the same answer. I'm going to skip a couple of slides in the interest of time. And so I'm just going to show you one example. In India, several research and conservation groups are involved in bioacoustics. One such long-term study using passive acoustic monitoring is carried by Dr. Robin. He's the guy that I collaborate with to do my young birder camp in his institute. And there, in a place called Kodai Hills, they've been doing long-term monitoring for many, many years. And I've got an acoustic signal here, which I'm not going to play because it's got many different birds. So, and these are birds that you're not familiar with at all, unless you are from that local area at 5,600 feet above sea level, you would not know these birds. So when you bring that data into BirdNet analysis, you need to tell where this data came from. You need to give you the lat long, lat and long of that location. When you do that, it actually gives you this data. It tells you these are two different time periods. It tells you, when it tells you the confidence level. In Merlin, you cannot set the confidence level of a signal. When it says that it's actually getting a signal, I think it presets itself at a very high confidence before it actually displays a certain bird. But BirdNet actually says, hey, look, you know what? I've got only 27% confidence on a brush bronze wing. So if you see one of those things, you will have to go and do a physical verification on those kinds of things. But there are birds which you can distinguish with a very high level of confidence. And you see this bird called white-bellied cholakeli. Dr. Robin actually classified that it's a new genus, which was discovered by Dr. Robin based on acoustic and genetic analysis. It was considered to be a short wing. It was classified in a completely different family, but they erected a whole new genus for this bird based on acoustic and genetic analysis. Okay, I'm about done, but there is something interesting about today and the presentation today. I'll show you that in my next slide. There's something about September and my talks, so you'll see why. September 20th, 2017, September 18, 2024, and I have got one more September I don't have a picture. So yeah, so it's about me in September and Washtenaw Nature and Bird Nature Alliance. So I'll see you in next September. So that's for sure. I'm working actually on a project which I won't give you any details. It's I'm going to claim that as a whole new approach to birding. I will leave it there. So I want to talk about that for the first time here. I hope it will be interesting. I'm going to spend about 6 months working on it. And so I'll come and present it right here. All right, thank you so much, folks. Appreciate it. I'll be happy to take questions. Yes, ma'am.
Have they tried to take one species of bird as a child and put it with other species and see if it starts speaking the language of the species that it's a different species that it's surrounded by?
Got it. I got the question. Did everybody hear what she asked? Yeah, exactly. Thank you. Thank you. Because it's a phenomenal question. It's been extremely well studied, though. I'll give you the answer. The question was, okay, I'm going to just use an example. I have the species called the cardinal, and I am going to take a baby that was born just now, and I'm going to bring that to a different oscine. At least let's be fair. It's got all the syringeal muscles. Let's give it a chance, right, to use up that syringeal muscles. So I'm going to choose another bird which is somewhat similar in size, maybe a robin, maybe, or any other bird that you would like to choose. Okay. No, okay, doesn't matter. So let's say that I choose a different bird, and I put that with the other bird's chicks as they are growing. Which song will this bird develop? That's the question. Am I right, ma'am?
Yeah, I'm wondering does it learn the
Yeah. Which song will it have, right? What vocalization will it come up with, right? Okay, that's the question. So let's answer that question this way. When a bird is completely isolated, I talked about Peter Morley's experiment, it will develop something called the isolate song, which is no comparison to any other bird that we know of. It cannot recognize its own species, right? Okay. On the other hand, when you do this experiment that we just talked about, it has been done many, many times for oscines. And some oscines, it doesn't matter. It comes genetically programmed. It doesn't matter what you do with it. But with oscines, when you do that, it will develop an isolate song. Wait a minute. What is going on here? I did not talk about that. I just had one slide about song learning. But thank you for asking, because it gives me a chance to explain a little bit more. When a bird is born, an oscine or a subossine, when a bird is born, it comes with a template. The template is empty, but it can only receive certain types of information in that template. That is remarkable. That's awesome. So when this bird goes to another bird, there's a mismatch in the template. It doesn't understand what's going on here. So it will develop an isolate song. Does that help?
Yes.
Thank you. Yes, ma'am.
Can you talk a little bit more about the bird that you were saying knows more than 1,000 songs?
Mm-hmm.
I don't know, I think I was just struck by that. And if you're determining the bird based on the song, if you have a bird that knows 1,000 songs, is that, I don't really understand. So can you just talk a little bit
Okay. So when bird research was going on, bird song vocalization was being studied about 15, 20 years ago, when white-crowned sparrow and the song sparrows were being studied, and they suddenly realized that they had a huge repertoire. Repertoire means having more than one clearly distinct song that it can repeat at a certain context, right? I'm not talking about a dialect. Within a region, within a habitat, it would have different songs based on the context. Right? Remember, I talked about the fact that context matters. That has been very well documented. So they had studied these birds, which had about 20 to 30. Then they started to study. Of course, there is a lot more people in this business now. They started to study. And brown thrasher, I do not know the actual, how did they actually come up with this research. But when they started to do research on the brown thrasher, they could actually come up with 1,100 distinct songs that it could repeat. It's not like a once in a while that it sings and it's gone. It's a song that it has learned and so on. So that's how they did that research. It is fascinating.
So I think we need to end the formal program so that the staff could
Oh, I know.
end at 7. But if you want to stay around and mingle,
Yes, sir.
more informally, I would encourage us all to do that.
Got it. Thank you so much.
Thank you again for coming.
Appreciate it. Appreciate it.